Today, we're going to continue learning even more derivatives. So let's do a quick review of what we have so far. In this top section, we've got all the core derivatives that we've learned about so far. The derivative of a power function, the derivative of an exponential function, the derivative of some trig functions, and then we learned the derivative of natural log. We also know the three important rules: the product rule, the quotient rule, and the chain rule. And we just combine the core derivatives with our product rule, quotient rule, and chain rule to get derivatives of more complicated functions. Today, we want to add to the list of derivatives that we know with the derivative of arctangent and the derivative of arcsecant. So this is the derivative of the inverse tangent function. So this is the derivative of inverse tangent. And the derivative of inverse sine. The other notation that we'll use for arctangent is tangent with a -1 for the tangent inverse. So alternative notation is to say the derivative of tangent inverse of x. The important thing that we recognize here is that when we write tangent to the -1 in this fashion, we mean tangent inverse, not 1 over tangent. If we want to write 1 over tangent, we write cotangent. Similarly, for arcsine or inverse sine, we can write this as the derivative with respect to x of sine to the -1 of x. But once again, we're not using the -1 as an exponent. It's a notation for the inverse. So here, the -1 is not notation for an exponent. So the -1 is not an exponent. This is just notation for the inverse function. This is the inverse as a function, not the multiplicative inverse, also known as the reciprocal. So we just need to learn these two derivatives. The derivative of arctangent is 1 over 1 plus x squared. We're going to start with just knowing that this is the derivative of arctangent. I haven't said why. I haven't said how we came up with this. This is just what it is. The derivative of arctangent is 1 over 1 plus x squared. The derivative of arcsine is 1 over the square root of 1 minus x squared. These are the two most common, but we've got sine, cosine, and tangent. And then, but for derivatives, we learned derivative of cosine, derivative of sine, derivative of tangent, and derivative of secant. Although we're not going to look at it today, you should also look up the derivative. This is a handy one to know. The derivative of arcsecant of x. And then we would write that derivative of secant to the -1 of x. So today I want to do a couple of quick examples of derivatives of arctangent and arcsine. And then we'll talk about where these derivatives come from. And this will also connect to the derivative of natural log being 1 over x. All right, let's take a look at an example. Let's suppose that we want to find the derivative, let's say f of x, is arctangent of 5x to the 3rd power. Let's suppose f of x is the arctangent of 5x to the 3rd power. We want to think about what happens to x. We see that we're going to be taking the derivative of arctangent at some point, and we know the derivative of arctangent of something is 1 over 1 plus that thing squared. That's our base formula. Let's see where the x cubed fits into this arctangent problem by thinking about what the first thing that happens to x. First, x gets cubed, and then we multiply by 5. Then we take that result and apply the arctangent. That tells us that the 5x cubed is going to be an inside function, and it's sitting inside the arctangent function. So this says that u is 5x cubed. Our outside function, y, is arctangent of u. And then the other piece that we're going to need is the du dx part for the chain rule. So those are all the pieces that we'll need to do the derivative of arctangent of 5x cubed. First, we have to make sure that we read properly the function and see the 5x cubed is being plugged into the arctangent. So for our derivative, we have to know the derivative of arctangent of thing. So the derivative of arctangent of something is 1 over 1 plus that thing squared. And the u in this case is 5x to the third. So this green part is dy du, and then the chain rule says multiply by du dx. Here we are applying the chain rule to an arctangent. The derivative of arctangent of u is 1 over 1 plus u squared. We would probably not write this way, all spread out. I have just a fraction times another fraction. It makes sense to put these into one big fraction. So there's a 15x squared in the numerator, and the denominator is 1 plus, we might as well simplify this. 5 squared is 25. X cubed squared is x to the 6th. So it makes sense to multiply all this out, or to simplify these expressions, or this expression. Any questions? Once again, the important thing is to make sure you read the function properly so you know which rule applies, because there's no way, reading the function is the only way to determine which rule you should use first. We want to make sure that we base that on reading the function and understanding what it says, and not just trying to visualize what's going on or try to come up with some kind of flow chart for how to read a function. Let's take a look at another example. Let's suppose that our function g of x is 5x to the third times arctangent of x. Here I'm following a similar pattern to what I did last week. I look at a chain rule and then I adjust it to a product rule. Once again, we want to read how things go. This is especially true if someone writes the function in a weird order, like arctangent and then 5x cubed, and they're actually multiplied. One of the reasons that we don't do that is so that we don't we make sure we clearly identify what the argument of the arctangent is. But reading this function, we first x gets cubed and multiplied by 5, and then we put that result to the side while we take another value of another instance of x and plug it into arctangent and multiply those two results. So that tells us that we should use the product rule. So here, the first, we're going to break we'll say the first is 5x cubed, and the second is arctangent of x. Now we need to use the product rule. So I'll need the derivative of the first. The derivative of 5x cubed is 15x squared. And the derivative of the second is 1 over 1 plus x squared. Now we're ready to use the product rule for g of x. So g prime of x is the derivative of the first times the second. So 15x squared times arctangent x plus the first times the derivative of the second It would be weird to write that fraction all spread out. It's weird to say 3/4 is 3 times 1/4, even though it means that. So we would probably put, it would make sense to put this term together in the second term together into one fraction. Any questions?
Yes, for Fisherlich. On this example, this is the product rule. How about the first example? What kind of rule? Was it like a chain rule? The first
That was a
one?
chain rule on the first example.
Okay, got it. Thank you.
In this example, we have 5x to the third being multiplied by the arctangent. In the previous example, we had the 5x to the third was being plugged into the arctangent. An important thing to remember about trig functions and inverse trig functions is that the trig functions need something after it. So we wouldn't want to just write arctangent. We wouldn't want to say f of x is arctangent. I don't know why I crammed it way over here on the side. Trig functions need an argument after them. Trig functions need something with the variable or a constant to come after them. Trig functions need something after them. Trig functions need something after them. So if we just write f of x is equal to arctangent, this means nothing. This is an incomplete thought. Someone stopped in the middle because there needs to be something right here. So f of x equals arctangent. This means nothing unless you say arctangent of something. This is an important thing to notice because when we have trig functions, we want to recognize that it doesn't make sense to say arctangent is a function. So we don't want to confuse arctangent of 5x cubed as arctangent as the first, and then 5x cubed is the second, because arctangent by itself doesn't mean anything. This is connected to why we would want to make sure that we write our functions that have this form, like sine, cosine, tangent, our inverse trig functions, the natural log function. We like them to go last in a term when they're all multiplied, so that we avoid writing something like arctangent x times 5x to the third. Because now we have to decide, and now we have to make sure that we recognize the 5x to the third is not part of the arctangent. And it makes sense because the x is in parentheses, so that's clearly attached to the arctangent. And if I write arctangent of 5x to the third, if I want the previous example, if there's nothing written there, then I have to read it as arctangent of 5x to the third, because arctangent on its own is not a thing. We can't use that. It has no argument. So trig functions need something after them. Writing f of x equals arctangent with nothing afterwards is meaningless. But if we write f of x equals arctangent of x, that's what we want to see. There needs to be something after your trig function. All right. One of the other things, on one of the other inverse trig functions you'll need is the derivative of arcsecant. So that one you're going to have to go look up. Let's talk about where these derivatives of inverse trig functions come from. Oh, just inverse functions. Sorry, doesn't have to be trig functions. Let's talk about how we find derivatives of inverse functions, not just trig functions, but inverse functions in general. What we're going to start with is we're going to write down what the relationship between a function and its inverse is. We want to write down the relationship between a function and its inverse. So an inverse function should undo what a function does. The inverse of adding 5 is subtracting 5. The inverse of multiplying by 7 is dividing by 7. Because if we start with a number, add 5, and then subtract 5, we'll be back to where we started. If we start with a number, multiply by 7, then divide the result by 7, we'll be back to where we started. So if f is an invertible function, if the inverse of f of x is f inverse of x, then we can say that f of f inverse of x is equal to x. It's also the case that f inverse of f of x is equal to x. If I apply a function to x and then apply the inverse to the result, we'll be back to where we started. If we add 5 and then subtract 5, we'll be back to where we started. Or if I do this in the other order, if I first subtract 5 and then I add 5, we'll be back to where we started. So our strategy for finding the derivative of an inverse function is to use the first part of this. We're going to use this, we're going to apply the chain rule to this part, to this equation, to find the derivative of f inverse. So I want to find the derivative with respect to x of f inverse of x with the chain rule. Then I'll find the derivative on the other side. The derivative of x is going to be equal to 1. So we're doing this. Find the derivative with respect to x of f inverse of x. This should be equal to the derivative of x, because I'm just taking the derivative of both sides. If two things are equal, then their derivatives must be equal as well. Here's how we're going to read. Actually, take a moment. Take a moment and read that this expression here, this function here, f of f inverse of x. Think about how the chain rule is going to apply. Now let's apply the chain rule. We're going to say that the inside is f inverse of x. So that's our inside function. That's the u. The outside function y is going to be just the function. Y is just the function f. The weird thing that's going to happen here is that if u is f inverse of x, then we need to find du dx. That's what we multiply by. And du dx is going to be the derivative of the inverse. The weird thing here is that the du dx is what we're looking for. This is what we're trying to find. We're looking for the derivative of f inverse of x. I kind of switched up my notation. This is the derivative of f inverse of x. So applying the chain rule on the right side, the derivative of f of u is f prime of u. So the derivative here is going to be f prime of f inverse of x. And then we have to multiply by the du dx, which is the derivative of f inverse, which is once again the thing that we're looking for. The derivative of x on the other side is just 1. So if we want the derivative of f inverse, I just need to solve for this factor. So the derivative of f inverse of x is 1 over f prime of f inverse of x. This all comes from the fact that the function the composition of a function and its inverse will be equal to x. If you do a function and then its inverse, you should be back to where you started. Let's see how this applies in one of the derivatives that we already know. So we know that the inverse, e to the x and natural log of x are inverse functions. E to the x and natural log of x are inverses of each other. That means if I do the natural log of x, and then I make that the exponent on e, we end up with x. It also means the natural log of e to the x is equal to x. That would make sense with the properties of logarithms. Natural log of e to the x is e times the natural log, or x times the natural log of e, and the natural log of e is equal to 1, because e is the base of the natural logarithm. But I want to focus on this one here on the left. I want to take the derivative of e to the natural log of x, and we're going to pretend that we don't know what the natural log is. So let's take the derivative of both sides. Because if two functions are equal, then the derivatives must be equal as well. And here we have the derivative of our inside function u is going to be the natural log of x. And our outside function y will be e to the u. The derivative that we're looking for, so du dx, is the derivative that we're looking for, and that will be whatever the derivative of natural log of x is, which we're pretending that we don't know. But we know it's going to come out to 1 over x because that's what's supposed to happen. So the derivative of e to the natural log of x is e to the natural log of x times the derivative of natural log of x, which we're pretending we don't know. And this should equal the derivative of x, which is 1. Now, e to the natural log of x is still equal to x. So x times the derivative of natural log of x is equal to 1. And so that's where we get the derivative of natural log of x is 1 over x. The reason I wanted to do this is that last week I told you that the derivative of natural log of x was 1 over x. And I just expected everyone to believe me and take my word for it. But once you absorb this fact and you start working with it a little bit, you start thinking, man, I just believed Leach when he told me that the derivative of natural log of x is 1 over x. Where does that come from? And you started questioning instead of just acquiescing to authority, which is the correct answer. Question everything. The more you believe it, the more you should question it. So here we are justifying that the derivative of natural log of x is 1 over x. It has to do with the fact that natural log of x is the inverse of e to the x, and that if you do a function of its inverse, you'll end up back where you started. We can do similar things with tangent and arctangent. We just take the inverse that we're pretending that we don't know, and we put it inside. So similarly, the tangent of arctangent of x is equal to x, and the sine of arcsine of x is equal to x. Similarly, the secant of arcsecant is equal to of x is equal to x. So this represents just 3 more derivatives that we are going to put onto our list of core derivatives that we just have to remember. This is like your times tables that you have to start remembering when you're doing arithmetic so that you could do more complicated arithmetic. This is just more derivative tables that you just have to remember so that you can put them all together to do more complicated derivatives. That, of course, raises the question, why do we have to find all these derivatives? And it's important to recognize that we're not doing all these derivatives because later on in your future career as a fill in the blank, you're going to be finding derivatives by hand with the product rule, quotient rule, and chain rule. But you are going to need to learn how to read, specifically read math, and you're going to have to know what all these symbols represent. And if we don't know how to do product rule, quotient rule, chain rule, then all this just gets in the way of learning what things mean. Imagine trying to learn algebra, but not knowing your times tables. Start doing algebra and it's like, well, first you have to do 3 times 5. Oh, hang on, let me get my calculator. 3 times 5 equals, okay. Oh, now I have to do 3 times 7. So 3 times 7 equals. By the time you go over to the calculator, plug stuff in and come back, you've forgotten what the point was. The point of being in the math class is to practice things to the point where you don't have to do the math anymore. You are trying to make this come naturally, and we get there through training. Also remember that when you're doing lots of math problems, when you start asking yourself, man, why do I have to know this? When am I ever going to need this information? That's only because it's starting to get difficult and you don't want to do it anymore. If I spent this whole class just doing derivatives of power functions, no one would ever question it. But it starts getting more difficult. Product rule, quotient rule, chain rule, put things together in complicated functions. Then we start asking, why do we have to do this? And that's the child's side of your brain saying, I don't want to do this anymore. Go play Xbox. And in the beginning, you're like, oh, be quiet, child part of my brain. I have work to do. Then the work starts getting difficult and you're like, oh, you know what? Kid's got a point. This is pointless. Let's go play Xbox. And then you high five your childlike part of the brain and you go play Xbox. And then when you start flunking your derivative tests, you say, well, Leach is just being a jerk. I'm never going to need to know this. And then I'm like, oh, dude, don't make me the bad guy. You're the one that signed up for this class. You know what I mean? So your job at this point is to know all these core derivatives. We just added 2 more, and I gave you 1 secret core derivative that you should look up and learn. And then practice putting all this together in product rule, quotient rule, chain rule. There's a great place to practice these problems using these rules at the very end of the chapter 3 in the book. So if you just go all the way down to 3.10, the section 3.10, you can roll all the way down to review exercises for chapter 3. Review exercises for chapter and problems for chapter 3. Find the derivatives for the functions in exercises 1 through 73. So it's just like do some derivatives, just training. This is where you go to the gym, and in problems 1 through 10, that's doing some bicep curls, and then 11 through 20, that's doing some bench press, 21 through 30, that's doing some lunges or some squats or something. And it just goes on and on and on. This is great training in reading what a function is trying to tell you and deciding what rule applies. Then everything else is, so now find for exercise 74 and 75, assuming y is the differentiable function of x, find dy dx, more derivative rules. Find the slope of the curve, find dy dx. Find the equations for lines tangent to the graph. That's all derivative questions. In the problem section, find f prime and find f double prime. More derivative questions. Any questions? Comments? Snide remarks? All right, that's going to do it for today. Tomorrow we're going to look at implicit differentiation. This is when x and y aren't being, when y is not being expressed as a function of x, it's being all mixed up in some kind of equation. Because that's another way that we describe curves, is with an equation. We don't always get to write functions, so we have to be prepared to deal with that. Any questions before we adjourn for the day? All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.